I will point out very clearly when we talk about the time-dependent part. The time-dependent part we will need whenever, when we need to explain phenomena of light-matter interaction, electron-photon interaction, things that you cannot, that are not DC change, meaning light is an electromagnetic wave, so it is intrinsically oscillating with time. Also, when we look at transport and scattering of electrons, we'll look at the time-dependent part. And so that we will kind of at least work through the formula for that as well, which will be the Fermi golden rule, which is the transition rates for time-dependent phenomena. We'll come to that later. Right now, this is time-independent. The idea, again, just to kind of summarize, I'll use. I think I should use a picture right away to highlight what we mean by this time-independent part. So, by the way, the notes on the set of slides, which is here. So the results I wrote down are included here in this set of slides. The example here is if I have, for example, instead of solving the free electron problem, let's say you have a particle in a box problem, single quantum well, and then you want to change it. Here you have solved it and found your eigenfunctions, eigenvalues, all that stuff, and now you want to change it and put in, so here are the eigenfunctions, let's say you have determined them and eigenvalues. Now you change it a little bit, you perturb it, but nothing is changing with time. So everything is it's independent of time, the wave functions, the steady state, all that stuff. So how do the values change? So now you break it up into a known problem, which you have already solved, and the perturbation term, which we're kind of trying to do now. So, and then based on this, I'll kind of skip through a few things, but essentially the end result after a few steps of derivation, which I would encourage you to kind of go through once, but essentially I wrote down today one of the things is the new wave function, or new states are the old states plus something, which is a linear combination of various coefficients and all that. And the new eigenvalues, this is the first order term that I kind of mentioned, and the full-blown second order term is something we need as well. So these are the new eigenvalues, the old eigenvalues plus the first order plus the second order term and all that thing. So this is a result which we can, I realize that this is a 4070/6050 class, and typically in many condensed matter solid state physics course you would not even invoke this, you can hand wave your way through it, but I think it's kind of the formulas, I mean you can use the formulas, and then as long as you know there's a layer behind it, and if you go through the derivation and understand it, great. If you don't, that's okay too, we can use this, right? And then that's because this is really at the heart of the problem we're trying to solve now. Okay? So what I'm also trying to do, and I know some of you have pointed out, and I did say in the class that I will post my written notes. Unfortunately, to post it, I need to finish it nicely, and it's in a somewhat of an incomplete state. Okay? And what I can do, I actually don't want to do that. I don't want to post it when it's incomplete, because there'll be some typos and all that, and you'll be like, I don't think I understand this part. But what I'll do is, since this is not being covered in the exam, I will post this over the weekend, and there may be some things which are not complete, but most of it would be reasonably complete. And what I'll do today is use some of the pictures from, just a second, let me bring that up while you're settling down. I'll use some of the pictures now, and in the process of understanding the band structure. So, by the way, so I just want to make sure that we are clear on what we are doing in this extra class. The first maybe 40 minutes we'll continue and finish the discussion we started in class today, and the last remaining half hour we'll do a review of some of the things we have done till now for the exam. So, okay, so what I'm trying to now do is discuss this picture of changed eigenvalues. I'd written that down in the class earlier today, and I'll use that and new eigenvalues and new eigenfunctions after the perturbation is turned on. Right? And the picture I want to kind of start with is towards the very end of the class today, we were looking at this sort of a picture that here's the gist of perturbation theory. You know, I mean, and this is, if you get it, you have grasped the most important thing about perturbation theory. Here's my exactly solved problem. Right? These are the eigenvalues, eigenenergies, and these are the eigenfunctions for the exactly solved problem. Right? And so the free electron, be it a harmonic oscillator, whatever be it, is the exactly solved problem. You got lucky with the Schrodinger equation here, and it was, you know, somehow we managed to solve it exactly, right? And that's great. So now we come in and we perturb the system. We add in a perturbation term. Let me. Okay. I think I have another picture here. Yeah. So this is the problem we're trying to solve again. So we have this set of eigenvalues, eigenfunctions. And then you change the Hamiltonian with a perturbation, and now the energies have shifted. Maybe they have gapped, you know, developed gaps and all that. And after going through a bit of this analysis, I wrote down that you can solve it in its full glory using the matrix method. You don't care about any analytical forms. Solve it completely with the matrix method, right? And the problem here, generally, if you want to solve it. You don't get an analytical expression most of the times, and except if you have 2 by 2 or 3 by 3, you'll get a formula which you can solve. Just to be clear, a matrix in one variable is a linear equation, right? And a matrix in 2 variables is a quadratic, and a 3 variables is a third order polynomial, fourth order polynomial, all that, right? So, and fourth order polynomial has 4 roots, so you have 4 eigenvalues on the right side. So that's the meaning of the matrix equation, right? So you can solve it, and we will use it today. And here the key new thing is this, W's, which are the matrix elements due to the perturbation. That's the new thing here. Right? And so these are typically referred to as the off-diagonal elements, because typically we'll see that the diagonal elements will mostly be, the W11, W22 will be kind of 0. And the off-diagonal ones will dominate, and those are the ones that will tweak your eigenvalues and eigenfunctions. So that's called off-diagonal term. So that's a full-blown matrix method, and the one which is analytical is again, you have the set of eigenvalues, and I was trying to kind of also say that one can picture it, these eigenstates or functions, as vectors, and then you turn on your perturbation and it kind of changes a little bit. You were trying to find a little difference. How much did it change? The eigenstates, how much did it change? And that's the formula that gives you how much it changed. This is the formula which I wrote down. Main points here is the final state is equal to the initial state plus a sum over all other states it interacts with. If it interacts, your matrix element is non-zero. That's what first determines whether there's any interaction between a state and another one, right? And if that's non-zero, then the coefficient, the strength at which it interacts, is equal to that divided by the energy separation. Right? If they're separated by a large amount in energy, then the change from the initial state is very small. This coefficient is very small. So energy separation plays a key role in determining how strong is the perturbation. Right? So closely spaced energies are perturbed more if they're allowed by the matrix term. Right? So yeah.
What causes it to go from in 7.21 a definite solution to an approximate solution in 7.22?
This is a great question for after class office hours. Right. But okay, maybe I'll just tell you what it is. Here, as long as you retain every state, it's exact. The moment you throw out some states, it becomes an approximation. That's really what it is. So, okay. So that's for the states. Here's the eigenvalues, and this is the unperturbed energy plus your matrix element with the unperturbed state itself, plus the cross elements with other states. And this is a matrix element squared in a numerator. Again, now it's squared instead of linear term. You can see this, whatever is sitting here must have dimensions of energy, right? Energy, right? So you have a matrix element has units of energy too. It's a wave function squared has dimensionless, and this is energy. This is the Hamiltonian term, so it's energy in joules or electron volts. So you have joules squared divided by joules. And in the denominator, what you have is kind of the unknown energy which you want to find. What is the new energy after the perturbation? So you either solve it, and so this becomes typically when you say I have solved this equation, what we mean by that is on the right hand side I have everything that I know. Right? And here I'm saying, well, this is kind of I don't know this yet, so it's still a polynomial equation, right? So this is much more accurate, and this is what's called the Brillouin-Wigner result. And if you say that maybe my energy did not suffer too much perturbation, and under certain conditions I can replace this by the unperturbed energy again, right? And then I know that, right? And that's called the Rayleigh-Schrodinger approximation, and so I replace it by the known unperturbed energy here. And we'll see later that for most cases it works beautifully, except you can see right away the big problem would be if these two energies become equal, then it blows up, right? And so you cannot do what's called degenerate perturbation theory. If the two energies are the same, you can't apply this. But this you can always apply, no matter whether it's the same or not, right? So we'll see that to understand the band gap opening in a periodic crystal, we would need to go to the degenerate or the matrix form of it. Okay, so that's kind of the main result of perturbation theory, and now we will start applying it. One more very important intuition, which I did mention, I'll repeat it again, is whenever states are allowed to interact due to the perturbation term, the end result is always something you can guess before even you do the math and try to understand all the details. So one of the things it will always do is okay. So because of this shift, the energy shift here, the way it looks, the way it ends up being, you have matrix element square, which is always positive, and then you have the denominator, and that sign determines which way it's shifting, right? And then because of the way they are ordered, you can see right away that if the unperturbed state, because of the perturbation, started interacting with a state which is higher than it, then you have the denominator. We can look at this one. Unperturbed state is lower energy than the one it's interacting with, which is EM or EN. And so this term becomes small minus large, so it's negative, so it gets pushed down. If it's interacting with a state which is below it, the matrix element square is still positive, but this becomes positive, so it gets pushed up, right? So energy, the delta E is positive, this turns positive. So essentially, all that it means that when I turn on a perturbation, and let's say this state starts interacting with both this state and that state, then this state will try to push it down, this state will try to push it up, and it has to reach some compromise. Basically, the total will be this interaction term due to that state plus that interaction term due to that state. And if the matrix element is much larger in one than the other, and they're equally spaced, then you can kind of guess which one will dominate here. If I have a state here and I have 20 states here, then basically this will get repelled by 20 times this compared to maybe one here. So the degeneracy can also play a role, and this will play a big role. We'll see later because this essentially determines the effective mass of semiconductors, because the bands repel. This will be a conduction band, this will be a valence band, and the states repel, and the amount they curve, the curvature, which is the effective mass that determines mobility, transport, is very much determined by the state repulsion. So how much they curve, how much effective mass they can, and essentially this equation will kind of tell you that directly, the effective mass and all that. Okay? Okay, so this is a quick summary of where we were in the class in the morning, and I'll continue from here and apply it to the free electron problem now, the 1D free electron problem. Very simple. And in your assignment, the last problem, which problem number 10, which is the 5th problem in this assignment, you are doing the 2D problem for this. You're going to apply. And what I've asked you to do is you don't have to apply this sort of picture. You can do it the matrix problem, and I would suggest you apply the matrix version to that. And I'll show you both right now. So for the 1D problem. Okay. Okay. So let's move in that direction. Then have to blank that off. So the problem we are now trying to solve is I had an electron on a ring, might and X, and let's say the electron, and the circumference is L, and we had already written down that the I will write it in a very rather, I'll write the psi. Let's first, I mean, I probably don't need to write down all the functions because we have already solved that. Energy of K, and we know that it's a quasi-discrete number of points with 2 pi over L, right? Separation, and it's a parabola. So I'll sketch that first. So this is now what you call as your exactly solved problem, because the Hamiltonian that the electron is seeing, the potential it's seeing is 0, so I've already solved it. And now what we're doing is we're going to, because the electron is going to be subjected to a periodic potential because it's in a silicon crystal or in a carbon nanotube or whichever. So now I add on my perturbation term to it, and I want to see how the energy is changed, how the wave functions changed, right? That's the question now, for the 1D. Right. So the first thing you generally do, here's the recipe, you find out the matrix element for any two states. Just any two states. What do I mean by that? You see that if I think of it in terms of matrices, the problem I have to solve is the following. I have, A1, A2, this matrix, which is my wave function, right? And I have the energy eigenvalues that I want to find, and I have A1, A2, where my new state that I'm trying to find is H0 plus W. Psi is E psi. So I'm trying to find my new eigenstate psi, and I'm writing my new state as a linear superposition of all the old states. Right. Now, the fact that I can write it like a linear, the new function as a new wave function as a sum of all old functions. Now, this has really nothing to do with quantum mechanics at all. This is a mathematical theorem from Fourier that any new wave function you have will be a function in X space, f of x, and I can always write it as a linear combination of a complete set of functions. I mean, that's really where it comes from, right? And you can always, this is guaranteed by mathematics, and there's no physics in it at all, right? The fact, I mean, there is physics in it. It just happens to be, that result that we're using. So, so again, this relation then is H psi, but in matrices is equal to E psi. Okay. And so, if I look at what are the terms here, what we have is H0 plus W, which is the perturbation, and then you have state 1 on the right side, and state 1 also on the left side. That is what we call as H11. Right? That's the first element. Then I have H22, H23, 3, and so on. These are all the elements of the of my Hamiltonian matrix. Similarly, the second term and third term. Why kind of do all that? I can just go and say, well, let me just choose some arbitrary term here, right? Some arbitrary term. And that arbitrary term, physically, what is the meaning of that arbitrary term? Here's the meaning of it, right? So I have one term here. Let's call it K2. Okay. This is state K2. Okay. And you can choose which one it is. Maybe it's 300 in this row and 300 there, right? And then I choose another state. Maybe it's here, or it could be anywhere, K1, state K1, right? And I take my Hamiltonian term, and I find this matrix element, K2, and this H0 plus W and K1. Right? So this is the most general term. Right? Does that make sense? I mean, K2 could be anywhere there, and K1 could be anywhere here. Right? And they could be the same too. I'm not placing any restriction on them right now. And the question is, what is that? And based on where K2 and K1 are, you find all your matrix elements. This is the most general term. So I'm going to find that now. Right? Now, let's write it because it's clearly sum of two terms. You can see I can write it as K1 Hamiltonian H0 K2 plus okay. So first things first. So what is this thing here, right? I mean, this is the solved problem, exactly solved problem already, free electron problem, right? So, and I look at it, so here's the Hamiltonian acting on a state on the right side, this state, right? And what does the Hamiltonian operator do when it acts on an eigenstate? It just gives you its eigenvalue, right? Does that make sense? So if I take this state and I say, well, my exactly solved Hamiltonian, which is the free electron, no periodic perturbation, no W, acting on that, is only going to do this. It's going to give me E of K2 times the state again. Right? That's the meaning of this, right? So it just acts on it. The operator, which was a matrix, acts on this state and becomes a number, which is the eigenvalue now, right? Does that make sense? So it spits out the number, which is E of K2. And then what I'm left with is K1 and K2, right? So you see, I mean, this is still a state vector. It's not going to go away. Now you've got to find this one, right? And what is that, right? This is very important. What is that? Now, that is clearly all these states are orthogonal to each other, right? K1 and K2 are orthogonal. So how do I write it? This is equal to 0 if they are different, but it's equal to 1 if they're the same, right? So I'll write it as a Kronecker delta symbol, right? Kronecker delta, which is K1 comma K2. Right? Kronecker delta is saying that if K1 and K2 are equal, this is 0. And if they're equal, they're 1, and if they're not equal, it's 0. That's the meaning of it. Is that clear? So, and physically, what this is, this mathematically it looks abstract. And physically, what it means, all that it means that this term only survives in the diagonal elements, right? Does it make sense? I mean, the moment you go off diagonal, you're looking at 1, 3 or 2, 5. So off diagonal terms, it's 0. That's physically what it means. Right? Is that clear? So that Hamiltonian matrix, you can see immediately simplifies, at least, well, it simplifies. So I can write now that my energy is E1 plus something, which I have to yet determine. But in the, that's my first term here. And 2 term will have E2, right, plus something which I have to determine. But the off diagonal term maybe it will have something, but it won't have E1 anymore. That's what we mean by that. Right? So it's not there in the off diagonal terms at all. Right? Okay, so now that's kind of the done part of it. But now this is the perturbation part, and that's where the new physics will kind of appear now. Right? So first of all, is that clear? This is. So now let's look at the new physics, and now obviously if you want to say anything useful about this matrix element, we have to write down what is that W, right? Because otherwise it's an abstract notion. And we started by saying here's the periodic, I'm going to put a periodic potential, which is a cosine potential in the path of this electron. I mean, classically you can imagine I have put in a, sort of a roller coaster in the path of the electron with a certain height and all that. That's really what it is, right? So we put that in. And the way we wrote is W of x is minus twice a strength, and the 2 will become clear very soon. Why we're doing it? Cosine of 2 pi over a. So 2 pi x over a, if you might. And so this term is what we said is the a is the lattice is the constant or the periodicity of this potential. And then we're going to write this as G, uppercase G, which is again 2 pi by A. So and we are going to later see why it would be called the reciprocal lattice vector. And right now it's just a parameter for us. Okay? Okay, so I'm going to take this potential, and I have to find this matrix element now, right? And that's what we need to do. So how do I do that? Let's evaluate it because. Okay, so K1, I write it down, minus 2 UG cosine of Gx, K2. Right? All right, so, and then physically, what does this mean? The matrix element, if you remember, what it means is if I know the wave function of 1, if it's sitting right there, I have to integrate it over the entire circle, entire x. Right? 0 to L. So physically it means over all space. If you're in 2 dimensions, go x and y. If you're in 3 dimensions, go x, y, and z, minus infinity to plus infinity, or 0 to L, where if you close the boundaries, right? So over all volume, all space, right? We must integrate it. And K1 would mean I take psi 1 psi of k1 complex conjugate with x. If it's sitting this here, I throw in my w minus 2 ug cosine of gx. And then on the right, I have psi of k2 of x, no complex conjugates, right? Does that make sense? I mean, that's really what the physically mean when we say what's the matrix element. So you take the wave functions of the k1, k2 state and plop in whatever you're trying to find the matrix element of in the bit in between and integrate over all space, right? So that's the physical quantity. And I just want to make a picture or draw. I'm going to erase this part. Draw the potential, because that's also pretty illustrative. And I'm going to draw it right next here. I'm going to erase this. That's okay. It's all right. We can erase it too. I'll write it back again. So you see, the minimum energy of the electron before you put the potential was 0. It was allowed to have 0 energy. So now on top of it, I'm adding a potential. So basically, my v of x was 0. And on top of it, I'm adding a potential which is periodic. So I'm going to sketch it here. So don't it may be a little confusing because this is k-axis, but I'm going to actually plot it versus x here. Just but the energy scale remains the same. Okay? Does that make sense? What I'm plotting here. So basically, this potential I'll plot w of x is just a pure cosine potential. Pure cosine potential at x is equal to 0. It reaches a large and negative value, right? So it reaches a value of what, minus 2 ug, right? At x is equal to 0, cosine is 1, so it reaches minus 2 ug, and then essentially after that it oscillates, right? I think I shouldn't have plotted that large. Okay, so I just space-wise. Okay, so I'll just put it here. That's minus 2 ug, and it oscillates between plus 2 ug and minus 2 ug. Right? You can change the value of ug and say that it's stronger or weaker or whatever, but it looks something like that, right? That's your perturbation potential, right? And just to kind of think about it, basically, so essentially we are, you can think of it as a classical path for an electron. I mean, this is an electron can go here, but you can see now that this is kind of a periodic array of atoms. For example, they were sitting here, and that's trying to pull it down or something like that. Right? So physically, that's what it means. And before even we do any math here, maybe you can tell me that if I turn off all quantum mechanics and go back to classical mechanics again, how will the energies change for the particle? Because you see. What's the minimum energy that particle can have with this additional potential now? Because earlier it was my earlier potential was just that, right? And then I added something like that now. So minimum energy is negative 2 ug. It can roll down and sit here and do nothing, right? That's allowed in classical mechanics, and we'll see in quantum mechanics it's not allowed. I mean, so what we'll see now is, but there will be something which will show up because I have a negative part in this potential, and the fact will show up as this energy, the minimum energy, will be pulled down. We'll see that the allowed energy will be pulled down, but it won't be minus 2 ug. It will be larger than that, and that's because of quantum confinement and all these other things. So because the wave function won't fit. But what we'll see now is because of this potential. Okay, so the band structure will change. This state will move down, and some states will move up, and all that. It'll create all these perturbations. Right? So let's find this term, and to find that term, I think you can see. Maybe you can help me to write down these two terms first. What is psi of k2x? How do I write that? It's a 1D problem, right? Particle on a ring. So yeah. So 1 over square root of the length, right, times I k2x, right? K2 is the index k2. So that goes there. Now psi star of k1, same formula, but psi star is a complex conjugate, so you get a negative sign with a k1, right? Minus I k1 of x. Right? So that those are your 2 terms. And finally, we throw that in. But now you can see right away, I'm not going to write it as cosine because these are all exponentials. I should use Euler formula and write cosine as a e to the power I theta plus e to the power minus I theta, right? So I use that and write cosine of gx is e to the power I gx plus e to the power minus I gx over 2, right? Have that. So that's why we had introduced the 2 in the beginning. So we got rid of that. And so I have a minus ug, which I pulled out from here outside. And then I have e to the power I gx plus e to the power minus I gx. Okay. And the 2's cancel. So go away. Yeah. Okay, so now you see, so actually if you get what I'm doing next here, one or two of these steps, this you maybe have encountered many times, but really this is at the heart of all things we are going to do next. The fact that it vanishes for some things and it doesn't vanish for some other things. And this is really the kind of the crux of the matter here, but it's actually very transparent. You can see now how it'll work out because you get 2 terms, right? There's this and that. And what you're really getting here is minus UG, 1 over square root length, 1 over square root length over length, right, of the circle, so the circumference. And let's look at the first integral here, 0 to L dx. And what you really get is e to the power I, k2 minus k1, and then you get a plus g x, right? So that's one term, and the second term is 0 to L. Same deal, k2 minus k1, but there's a minus g here. Those are the 2 terms again. So again, a sanity check. Whenever we're doing these things, this whole thing, it's a matrix element, should be units of energy. You have energy sitting here, length in the denominator, but you're integrating over x, so that's still energy. So that's all good, right? Okay, so now maybe you can tell me how will this term look, and then that's I want to kind of ask you this question: what will happen to this term now? What will that look like? Right? So e to the power I, k2 minus k1, and then there's a plus g. Forget about the second one, just this term. What will you can? It's a simple integral. You can just evaluate the integral, right? But this sort of integral. Just to kind of remember the k2 and k1, what are those things here? K2 is 2 pi over L times some integer, maybe n2. 2 pi over L times an integer. K1 is 2 pi by L times n1. That's also an integer, right? And G is a reciprocal lattice vector, is 2 pi over A. A and L are different. A and L are different in what way? L is the total circumference, and A is the distance between 2 periods. So L is some big integer times A, right? And this is a large number. It could be very large, 10 to the power 20 or something like that. It's the number of atoms in the crystal. So L is related there. So anyway, so when I take this integral, first things first, you can see right away that if this vanishes, if k1 minus k2 minus k1 plus g is 0, right, then e to the power 0 is 1, right, and dx you are integrating, you get a length, so this thing is just kind of gives you minus ug, right? And you can prove, and I'm not trying to do that now, but you can prove now that if it doesn't vanish, the integral would be 0. And it has to be because it's an oscillating function, and it will have a certain number of periods around once you go around, and equal number of positive and negative halves, it will go to 0. So now what we get here is again a Kronecker delta symbol. But then it kind of tells you, right? Let me write that down. So using this, and what we get is this matrix element between k1 and w and k2. Is minus Ug, which is the strength of the potential. Actually, it goes between +2 and -2 here, times. So you get 2 terms. You get a Kronecker delta. So L will get absorbed because when e to the power 0 is 1, you integrate, you get a L here, L, they cancel. So you get a Kronecker delta of K2 minus K1. And the way I write it now, you can see comma minus G plus Kronecker delta K2 minus K1 comma plus G. Okay, so essentially there are two vectors. One of them, when K2 minus K1 is equal to G, it vanishes, and when K2 minus K1 is equal to negative G, it vanishes too, right? But it can't happen at the same time. If K2 minus K1 is plus G, it cannot also be minus G, right? So that's what I'm trying to say here. Okay, so that's kind of the end result that we're getting, and now you can look at this and say, what does it really mean? It's right away. It's what it's telling you right away is what are the states that are getting coupled by this periodic potential. That's sitting right in front of us now. So after evaluating that matrix element, it's saying that any states 2 and 1 which are separated, if the difference between them is equal to plus G or minus G, meaning the magnitude, the difference is equal to this reciprocal lattice vector, they are going to be coupled by this periodic potential, right? Does that make sense? I mean, that's physically what it's saying, that if K2 minus K1 is plus G or minus G, you are going to get coupled. The strength of that matrix element is minus UG. It's also giving you the value of the matrix element right away. And that's kind of the first, I mean, the most important part of this perturbation theory result, that we find out which states are getting coupled, right? And we found that now. And it's very precise. It's saying that as long as the states are separated by the reciprocal lattice vector, which is 2 pi by the lattice constant or the distance, which is, they're going to get coupled, right? And what is also saying, very importantly, is if I take any other states, I take this state and this state, they're off, they're not differentiated by G, they're not going to talk to each other, they're going to be unperturbed. Those things are not going to talk to each other. That's physically what it's saying, though they don't get coupled, right? But this state will get coupled to another state which is G out there. Right? Does that make sense? So as long as they're separated by G, they get coupled. What does that, is that clear? Any questions here? So you can, kind of see. So I'm going to go back now, erase this, and look at the matrix. And I will post this write-up as well in your, in the updated set of notes. So what it also means is if I choose to work with a restricted number of states here, let's say I only choose to work with this many states in my Hamiltonian matrix, and you can see that as long as they're separated by G, they will get coupled. And the separation, in some sense, I mean, if you look at it, let's say I go down, I look at 0, state 0 here, and then I have to go to plus G or to minus G to find states that it gets coupled to. And so essentially, if this is 0, then I get 1, 2, and all that. So maybe my state G is here, which is 2 pi by 100 times that 2 pi by L, if you might. And so what it really means is only terms. So instead of writing 0, maybe I should write it in this way: state 0, state 0. Here's the matrix element for 0, but there'll be only one other term in this whole row, right? One term with 0 plus G, and another term which is 0 minus G, which will be non-zero, and everything else will be 0 here. Does that make sense? There are only two terms it's coupling to, right? In this whole band structure. Yeah.
Now what about the center one?
Yeah, the center one is its original energy, whatever is the unperturbed energy.
Yeah, but it wouldn't be 0.
The value would be, so for particularly for E, for state 0 here, it will be 0 because it's indeed 0. But if it's not, it will be unperturbed value. But what I'm trying to say here is what you end up getting here is what's called a band matrix. You get a band of energies which are separated by plus G and minus G, right? Which are non-zero terms, and everything else is 0 in that matrix. So, and you can choose to work, and you can actually set it up to solve a very large number of states, but we are going to really concentrate on a few now. But that's the picture. That's what it does to the matrix, right? The periodic potential. Maybe I'll just briefly mention that one of the very important things to get from here is why did it happen this way? And the reason for that is because the periodic potential is essentially, you can think of an electron moving in the periodic potential as it can provide in momentum space, in k space, this much energy change to two states. So for example, if we start with k1 here, it can provide a momentum change of g because it scatters. That's the crystal potential. That's the kind of, and then it can give you UG of energy, and it can scatter an electron from here to there. That's physically what it means because of this periodic potential. So it interferes or it diffracts with that state, and it gets perturbed because of this reason. If it's not matched with this periodicity, it doesn't get perturbed. So that's physically what it's trying to say. Now what we can do is choose some of the energies here and find, well, which states should we focus on first, right? So we can choose any two states here, EK, E1 and E2, and find the new eigenvalues because of this perturbation, right? Because we have already found out the heart of the problem is the matrix element for any K1 and K2. We already found that, right? So I can apply this and find out the new eigenvalues for any states. But remember, one of the results of this, kind of the analytical part of the perturbation theory was that the change in the energy, or the perturbation, if you might, goes as the matrix element squared divided by the difference of the two energies that are interacting, right? It goes as this term. This is I'm saying this is the change. This is the result of the perturbation theory. And now you can see that we have already identified which terms are non-zero. This, as long as this k minus that k is equal to g, I have a non-zero matrix element. But now I look at the denominator and say, when this periodic potential, which states is it going to kind of affect the most? Which states is going to affect the most? And right away you can see that this will be maximized when these two states are the same energy, right? The same energy, exactly the same energy. And that's degenerate. That means the two states must be degenerate. And now you can, is that clear? So as long as these two states are the same, or they're very close, then this term is maximized. So I want to kind of zone in on the most important perturbed states first, and then we go to the weaker ones later. So here it's essentially, now the question is, can we find two states in this whole band structure of free electron band structure such that they're degenerate, meaning they're the same energy, and they're separated by g, right? That's the question we want to ask now, right? Because otherwise they don't interact. And that means essentially you take this arrow and for example, if you're looking at this state, that arrow length is not changing, but that's very well separated in energy. So you kind of shift the arrow, and you find there'll be only one choice left for you, right? And what is that choice? That choice is when you get g over 2 and minus g over 2, right? Those are the states. Does that make sense? So they're separated by g, but they're degenerate too. So that really restricts your choice to maybe this state and that state. And these are the two states that we want to kind of focus in on first. Is that clear why we chose this? So, because I think this is, I've not drawn it properly, because this is clearly not separated by g, right? This is g. What did I do here? Why did I? All right. Let me resketch it. I want to start with still that axis. Okay, k, and here's the parabola. And all right, so let's say that is the length of g, and what we want is, well, if that is g, then right, that's g. Okay, and that means that this state must be g over 2, and this is minus g over 2, right? And they are degenerate, right? That's really what we mean to say here. And so the two states I'll focus on now are plus g over 2. You can see the k is given precisely by plus g by 2. And this state is precisely minus g over 2. So those are the two states I want to focus on and see what happened to those states first, because they got hit most by the perturbation. Because of two reasons. One is the matrix element is non-zero. The second is the denominator is as close to 0 as possible. It actually is exactly 0 here, right? So I want to find what happened to those two states. And how do you find that? You can see the first thing I'll do now is I'm going to go to my matrix version and say that I'm not interested in all other states right now. I'm going to completely neglect their presence in this problem. Right? I'm going to zone in, and I'm going to look at only these two states. My whole quantum system now is composed of two states, this and that. Right? And then I want to find what is my matrix, and I solve it, and find the eigenvalues, and find how did the eigenvalues change for these two energy states. That's what I'm going to do now. Does that make sense? So what is the unperturbed energy? Maybe you can tell me what is the unperturbed energy here without the periodic potential. That's, is a square, k square by 2m, where k is g by 2, right? And so we write that down, h square g by 2 whole square by twice the mass of free electron. And that we're going to just call as big, this uppercase F. We're going to just label it as F because it will appear many times. It's a characteristic energy scale here in this problem. So we take that. And here's how I'm going to write the matrix. And you can hopefully see the reason it's being written this way. A1, A2 is equal to E, A1, A2. See, it's a 2 by 2 matrix. For this particular reason, I've chosen only two states. Right? You don't have to, you can choose more, but this is the simplest, right? We're going to start there. And it will give us the band gap right away, right? So of the situation, the band gap of this material, that will develop in this density states here. So, so the way you will create this state is I write it as, I generally kind of always like to label it this way, plus g by 2 and minus g by 2. These are my two states, right? This is outside the matrix, just a labeling index for me, plus g by 2 and minus g by 2. So if I look at the diagonal term here, what should I write? Yeah, F. Diagonal term means, what's the unperturbed energy of this? That's just F, right? Because that's basically, if you remember, H0 plus W and plus g by 2 and minus g by 2 here. And W, because, plus g by 2 and plus g by 2 here, right? So a W gives you 0, H0 gives you F, unperturbed energy. This is the diagonal element. So you just get F, right? And here also you just get F. Right? These are the unperturbed energies. What do I get here? Negative UG, because they are separated by exactly G, right? This minus this is plus G. Right? And if so, your matrix element is minus UG.
Would it be negative 2 UG because those two deltas add to 1?
It's a good point. Actually, it won't, because it can be either plus or minus. It cannot be both. So it will only be minus UG all the time. Yeah. So you get a minus UG and a minus UG. And the off-diagonal terms are always complex conjugates of each other, and here they're real, so the off-diagonal elements will be the same. It's a Hermitian matrix, if you might. But anyway, this is, if you're not comfortable, I want to just pause here and make sure that you're comfortable with this picture, what I did here. So what did I do? I started with my eigenvalues that are exactly solved, found the matrix element, and precisely determined which states will get perturbed. Right? And I found that every state will get perturbed because this will start talking to a state that's plus G and minus G, right? But then among those states, which one will get perturbed the most? That I get from here. It says, well, as long as the energies are close, they're the most perturbed, right? And then I find the ones which are degenerate, which is very, very large perturbation. And we're trying to find what are their new energies and what are the new eigenvalues. Now, that's what we're trying to do now, right? So, and how do I quantitatively solve that? I kind of write down the Hamiltonian matrix again, and we realize that this is the unperturbed, and here's my off-diagonal perturbation terms. And yeah, right.
So when they're degenerate, they're identical, your delta E is going to go to infinity.
Yeah. No, it won't. And it's a good point. If you are applying Rayleigh-Schrodinger sort of picture, if you are applying the Brillouin-Wigner picture, where your energy here is really not the unperturbed, but you need to find it. It's not. It doesn't blow up. And so if you apply the Brillouin-Wigner picture, you will get the right answer using this form too. It won't blow up. But if you apply the Rayleigh-Schrodinger picture, the Rayleigh-Schrodinger picture gives you a feel for how much you will have, how much it will perturb. Okay, so just to be clear, this is because we made that approximation, and this is called non-degenerate theory. It's only applicable when you don't choose degenerate states. If you choose degenerate states, you must not write it this way. This is the unsolved energy now. You've got to solve this whole thing again.
That's because when you use the unperturbed energy and it's degenerate, your EM just becomes your unperturbed energy, and you get, no, it'd be the other way.
This one becomes the unperturbed energy.
Yeah.
So yeah, so I'll point it out in slides a little bit later as well. But no, that's a good point. The fact it's blowing up is just because you try to make life easy for you, and then you suffer the consequences when you deal with the degenerate situation, right? That's really what it is. It has no problem physically or mathematically because of that approximation. Yeah. But anyway, so this is probably one of the easiest Hamiltonians you can solve, essentially, or rather matrices to find eigenvalues for, right? So what does that do? You take, right, f minus ug and f. So essentially you take this to the left side, and when you pull this, it's a number, but then you have to have a 1 0 1 1 0 0 identity 2 by 2 matrix, right? And so what you get is, here's the equation. You get f minus e minus ug and f minus e, a determinant 0, right? That's what you get here, right? So what I did was I multiplied this with just to be, in case it's not clear, I did 1 0 0 1 identity matrix, and then I took this and subtracted term by term elements from there on the left side, and then I say that essentially my equation then is this times a1 a2 is equal to 0, right? The 0 times a1 a2, if you might, right? Just 0, right? And then this is only true if the determinant vanishes, right? So that's what we're doing here, and the determinant, okay, so is equal to 0, and it's easy because you do that times that minus that times that, so f minus e whole squared is equal to ug squared. That's the solution, or rather that's the answer. And what we are after is what are the new eigenvalues, right? That's what we're after. What are the new eigenvalues after the perturbation? And you can see from here what are the eigenvalues. Strip off the square root. You get two eigenvalues. This is the second order equation, e squared. So you get e plus and e minus, and they are the original energy, unperturbed energy, and plus and minus ug. That's your. Those are the two new eigenvalues, and what has happened is this state, these two states, one was, both of them were f because of the perturbation. One has been pushed up to f plus ug, the other has been pushed down to f minus ug. And now in between them, there is a gap, which is e plus minus e minus, and that's 2 times ug. There's a gap between them, so the gap may not become immediately clear, but I'll just sketch some pictures now and show that. So that's just the eigenvalues, and you can also find what are the eigenfunctions, because then you have to find out what is a1 and a2, right? And that can be done. And let me just show you this, and I'll try to finish up this part of the discussion with this point here. So that's eigenvalue, and eigenfunctions will look. Okay, let me bring that up. Where was that? Oh yeah. Okay, so I will again, as I mentioned, post this. So I've written this up, so read up later. And we add the periodic perturbation. Here's our nice periodic potential. Okay, and then we find our matrix elements, and then we did that, diagonal elements and off-diagonal elements and perturbation. And now here's in pictures what I was trying to mention earlier, that so this state and this state are talking to each other now because of this periodic perturbation, and this are also talking, but we're not talking about them right now, right? And then when we saw what happens to these two states is here's the thing. So essentially, you can apply the same technique to all other k states now. Right? Same technique, all the k states, and you find what are the new eigenvalues. When you plot them, here's how it's going to look. Here's the dashed line, which was the original eigenvalue spectrum. Okay? And here's the solid line, which is what happened after this perturbation was turned on. Right? So, and you'll see there's a missing range of energies there. Right? So that's the gap we're talking about. And the gap is found exactly at g/2 because that's where the perturbation is the largest. So that's where it kind of splits the most. And the splitting is exactly, for this potential, is exactly 2 times UG, which is kind of the, remember plus minus 2 UG was the strength of the periodic perturbation. And then so that all these energies were initially allowed, and then when you turn this on, it splits, and energies bunch up a little bit here, bunch up a little bit here. Still, the total number of states is exactly the same. It has not changed, right? But we have reordered them in energy space now. So it's pushed them up. So you can see now, here maybe I had a little low density of states because I had very few, but now I kind of bunch it up. Density of states increases. So essentially, I don't change when I apply periodic potential. I don't change the number of energy eigenvalues allowed. I just change where are they located in energy. I change the density of states, not the total number of energies. Okay, so what I wanted to show is you can analytically and exactly find what are the wave functions for the two states too, because all you need to know are the two coefficients A1 and A2. And from your matrix, if you're using MATLAB Mathematica, you can ask it to plot your eigenfunction in real space. How will it look? So for the 2x2 matrix, it's exactly solvable. Your eigenfunctions look like this, depend on the matrix elements, and which we know already. Take that, and you write your plus state, which is the upper state here, and the minus state, which is the lower state here, and you can compose your wave function. And I will kind of say that when you evaluate it, what you get is the upper state looks like a sine g/2. And the lower state looks like a cosine g/2. And now I want to plot it and say that here's my upper state, the energy plus energy plus UG. And when you say it's sine, you can see its minimum is at the minimum of the periodic potential. So that's the state that was pushed up. The state that was pushed down is a cosine. So it basically, its maxima is where the cosine is, which is minima here. Does that make sense physically? So those are the two states. The red one is the upper state. The blue one is the lower state. And you can look at this picture and of course I understand now why this is at a higher energy. Because those electrons are piling up in regions that the potential is high, right? And therefore its energy is larger than it was before. These electrons are piling up at a state where energy is low. This is lower than 0, remember. This is basically the cosine potential. The 0 is what it was before the perturbation, right? So they pile up at the low point, so this is your this state has lower energy, that state has higher energy, and you can see exactly why, right? So this is kind of the first result from the perturbation theory, that you can get the gap, and the gap happens to be kind of related to the coefficient of the periodic potential, and it rearranges it. You could have solved it analytically, and you could have done quite a other things. In the next class, after the exam next week on Thursday, we will look at very close to these states. And now you can do all this calculation by yourself. It's you don't. So what you can do is take the. I'll just look at this particular problem. So you can kind of set it up as for any k. Okay, here's my energy band structure for a free electron. right? And then I kind of evaluate some of this stuff, and I find my function, new functions after I've turned on the perturbation for any 2 k states. You can do that, and you can plot. Wait, what did I do here? E0. Just a second. All right, so I'm just plotting the positive part of the case here, and here's my periodic potential. Okay, sorry, the strength of the periodic potential is up there, and this is my positive half of EK diagram. You can turn it on, and you will see it will do all the calculation for you. It's just a 2 by 2 matrix. You can do it by hand. You can write the formula, and you just plot it, right? But it kind of creates the whole band structure for you now. This is the new band structure. Right? One more thing you can see right away is this state, which was at 0. Is at a negative state now. It's negative energy. Could you have said it without even, so is it clear why? Or because this state is interacting with 2 other states, right? One is at plus g somewhere there, the other is at minus g, which is somewhere there, and both states are above it, right? So they're both going to push it down. Right? Does that make sense? So it has to go negative. There's no other way, and the amount of it has to go down. We'll talk about that in the next class. More importantly, the splitting here is exactly, so you see UG, I've turned it up to 2. Splitting is exactly 2 times 2, which is 4, because the gap is 2 times that. Right? So at all points. Yeah?
So you said there are 2 ways to solve this, one being the matrix way, one being the analytical way. But the derivation we just went through seemed to use both. It seemed to use the analytical way to solve for what the matrix should be, and then plug in the values in the matrix.
Good point. So actually, we got here. It's a lucky situation. You have a 2 by 2 matrix, and you can ask your solver to solve for the matrix. It's a 2 by 2 matrix. You get a but 3 by 3 you get a third order polynomial, fourth order. Those are not typically analytically solvable. Some of them are not, right? And so I'll just kind of write this part down, and we kind of make the discussion end today. I'll just write this part down now, saying that this is the matrix method, and it will always apply no matter how many terms you have. Now the analytical method. All right, I'm going to erase that. The analytical method will give you exactly the same way too, but it will look a little different. Let me just show you that. Okay, so analytical method would be, I'm going to consider these 2 states, okay, just these 2 states, okay? And I'm find, well, what are the new eigenvalues, right? The new eigenvalues, I'm still writing approximate here, are old eigenvalues. What are the old eigenvalues of this one? I'm going to look at this one. What's the old first unperturbed eigenvalue? F, right? So okay, what's the formula? New eigenvalues are unperturbed eigenvalues plus unperturbed matrix, the first order term, plus if I'm going to only talk to one other state, there's only one other term here. If I was talking to 5 other states, there'll be 5 other terms here, right? There's only one other state. So what will that be? It will be, let's write it this way, plus g by 2 w and minus g by 2, right? Whole squared divided by well, okay, plus g by 2, let's say. Okay, this is what we need to solve here. Does that make sense what I'm writing there?
Okay.
Right, and then it turns out that that happens to be exactly 0, because we found that this, if these 2 are the same, we get a 0, and this happens to be exactly f, right? And that thing happens to be just exactly UG, which is the strength of the perturbation, right? So you get UG squared over E minus, and that is just F, right? So now you got to solve this thing. This is your analytical form. And you see here, you get exactly the same, because you can take this here, and then you multiply, you get, or approximate if you might, but actually this happens to be exact, right? So you get the same deal here. So in other words, this term, I mean, this result, which is the Brillouin-Wigner result, is kind of already giving you your full matrix solution, directly. It's giving you that, if you solve it. So. Yeah.
Why would you use the minus g over 2 also as another term in the sum?
Very good point. So actually this is a great point. So this is a question that why am I not using my, so what the perturbation theory tells you is you got to choose one state first, right? And then look at all the other states it's interacting with, right? So here plus g by 2 state can interact with minus g by 2 state, right? And it can interact with one more state. And where is that? That state is g by 2 plus g, right? Because remember there are two terms, k2 minus k1 can be plus g or minus g, right? So I can go to the left by g or to the right by g, right? And that state is still there, but it's very high in energy, right? Does that make sense? I mean, so I must have that, so that's when it will make it exact, right? But I'm throwing that out. Why? Because that is very high in energy and my denominator would be kind of very large, so that perturbation would be very small. That's the approximation here. But you don't have to make that approximation when you're solving analytically. You can consider all of them together. And that's what I did when I plotted, I was showing you this mathematical plot. I actually considered all of them. And when I say all of them, it's just two others, right? I mean, so it's not too many really. So, yeah.
Could we think about this wrong, but at that condition, do you have a standing wave?
Yes, exactly. So, so that's when the wavelength of that electron becomes exactly resonant with the wavelength of the perturbation. So these are two standing waves, and the upper state is when they are piled up at the node, I mean the highest point of the perturbation, and the lower energy state is when they're piled up at the lowest energy of perturbation. But both are the electrons have formed standing waves now because of the interference and the diffraction of the because they have strongly the wavelengths have become resonant now for the electron and the crystal. So I'll actually carry on with this after the exam, but I think if you got the basic gist of it, I think we made a great advance today with this, because this is, and then you saw already that, you know, when this went down, it will curve like that, you know, and so this part will curve and all that, and that curvature is what's related to the effective mass, you know, and how fast electrons can actually move in the crystal and all that. Those curvatures are very important. And in your assignment, you have a problem where you are actually given a 2D. So essentially, one of the problems is, you know, where you're given a cosine potential and say what is the band gap, right? In a 2D problem. I think you can apply exactly the same trick, but now you have to be a little careful with what states you consider, right? And because that potential, you've got to kind of split it and find out what is a corresponding result for the 2D problem, right? If I have a k state in 2D, what other k states will that potential couple it to, right? And then you create your matrix, and that's how you get the band. You can calculate your entire band structure there, but I think asked you for the band gap primarily, which means this part of the problem, right? So yeah. Okay, so I know you probably have more questions, but if there are any more quick questions, I can answer on this, but I want to stop here and then just do a very quick recap of some of the things, and hopefully we'll get a pizza soon. But yeah. Any questions? And we'll get some practice on this, and as I just want to make sure I decided to take this approach in the class, because typically people don't talk about the perturbation part, like, oh, well, this is what you get in the end, and get 2x2 matrix. But I think this is kind of illuminating to see, you know, why we chose those states first, right? I mean, that's very important here. Why we chose only a restricted set of states. And then after you realize that, I mean, typically what you do in a calculation, you can choose a number of states around here, and because you know all the action is happening around here, and you can, you know, calculate them, can increase that window and all that sort of thing. Yeah, there was a question. Yeah. All right. Yeah. Yeah. Oh, Connor, no questions. Okay, good. So, all right, Austin.
Yeah, I was just wondering on the delta functions down
Yeah.
here. What is that subgroup beside one? Is that K?
Okay, so let me. So actually, this is the right. You mean the Kronecker delta, right?
Yeah.
K2 minus K1, comma, plus G or minus G. That's what I meant. Meaning when this becomes equal to plus G or this becomes equal to minus G. That's what I really meant. Right? So I think I had it the other way around, but the physical meaning is comma, this comma minus G. That's what I meant. So and you know, as an extension, if your periodic potential was not the simplest cosine potential, if it had cosine of g1x plus cosine of some other g2x, another periodicity, you can see that this state will now start getting coupled to this plus g and minus g1 plus g2 and minus g2, all that stuff. So that's the picture. That's how all the band structure of all solids, metals, semiconductors are calculated. You kind of find that coupling, find the strength, and then find the eigenvalues. How did that change? And the eigenfunctions and all of that you get from the direct calculation here. Okay, so what I want to do is kind of do a brief stop here, and I can go over a few things about the exam. Let me do that in forms of the slides, because if you are reading through your slides, which are written in sufficient detail, I would say that for the exam, if you want to let me just go back. So the free electron problem is what we started with in this course. Okay, so we kind of spent some time trying to introduce the ideas of quantum mechanics and how electrons, what are the rules they are subject to, and we kind of went through a little bit of the historical path that it took, but essentially we came up with the final picture that I need to solve the Schrodinger equation to find the eigenvalues of electron, what are allowed energies of an electron in any situation, be it free, be it in a hydrogen atom, be it in a crystal. Right? I need to solve the Schrodinger equation, because that's the Newton's, or rather that's what tells me what are the energies allowed. And the reason for that is because it's a wave. I mean, electron has a wavelength, and it's forced to kind of, and the Schrodinger equation kind of combines the wave and the particle nature of it in one form. And because of that, we were forced to say that, well, I can't just say here's the x of the electron and here's the momentum of the electron, but all that information is in the wave function. Right? The wave function now captures its state of motion, or state what energy it is at and all that. So that's what we mean by the state. And once we realized that, we kind of went back and looked at some of the classical results, and one of the main classical results was the Drude result of conductivity, and that's an important result, because you have seen that I think last week we did all the quantum and came back and said I can explain Drude's law again, using quantum mechanics now, right, instead of classical mechanics. How did we do it classical mechanics? That's a very important thing, meaning you have a Newton's law of motion, you have force, rate of change of momentum, right? Force is equal to rate of change of momentum. In the notes, minus E is equal to Q, which is negative of electron charge. And then in Drude model, you have the damping, right? The damping, which is because of scattering and collisions of the electron in classical picture. And when we solve this, we get the conductivity expression. So this is a very important result, and I would say just make sure that we are very comfortable with this result. Conductivity is given by this n e squared tau by mass, and there's an effective term called the mobility, and they're related through this relationship, right? So it's kind of an important relation. And we talked a little bit. You solved an assignment problem about the AC problem. You can explain classically, just using the fact that J.J. Thomson had discovered the electron, and it's a classic. If you consider it to be a classical particle, you can already explain all these things: electrical conductivity. You can explain reflectivity of metals. That was first assignment. And I'll kind of skip a few of these slides now. But kind of the main point I want to say is it could explain a few things, but then there were a few big problems that you couldn't. For example, one of them was a specific heat of electrons, and how it predicted a specific heat that was way larger than what is actually measured. Actually, people couldn't even measure any. It was 0 compared to what was, the classical picture. So specific heat, and more importantly, the problem was what's called the existential problem. And why are some materials metals? Why are some semiconductors? Why are there some insulators? That this Drude picture gave you no answer on at all, right? I mean, it couldn't explain that picture, right? And that's why we say, okay, now we apply quantum mechanics to it. And so Arnold Sommerfeld's model, what he did for the first time was, all that he did was it said that electrons are fermions, and therefore they are subject to the Fermi-Dirac distribution. They're not subject to a classical e to the power minus energy by kT, like a Maxwell-Boltzmann energy distribution, but they're subject to the Fermi-Dirac distribution. What does that mean? It means in one state there cannot be more than two. That's the Pauli exclusion principle, right? The moment you just apply that and nothing else, you don't need to apply band structure and all that, you immediately resolve the specific heat problem, and then you could show that it is, that's what you're doing in your assignment, right, this time, right, the second assignment. But then you could then explain also the, okay, so we went through quite a bit of the quantum recipes for it. So please be comfortable with that, and I will definitely not ask any questions where you need to solve like a problem. Most of them will be related to the free electron problem, where you don't need to kind of know, well, here's the solution of a Hermite polynomial or something like that. I will not ask that. So that happens with parabolic potentials, and I'm not going to ask that. It's more conceptual, that if I have electrons moving in 3D or 1D, so dimensionality is a very important point. And one of the things I think also Reed mentioned is the density of states, which is a very important thing, because once you put an electron in a 1D circle or in a square edge, so that immediately discretizes the allowed values of k, right? It says only certain k's are allowed, right? And then the density of states, how do you go from the fact that, so here's a very important distinction between the energy states and the k states. The k states for all materials are exactly the same. The k state is always the same. It's always separated by 2 pi by L here, L there, there. And now the energy that's associated with that is dependent on the crystal potential, with what sort of thing, but the k space is like the same for graphene, for any 2D material, or any 3D material, it's always the same, right? It's just a grid, okay? And then we go out and say that I want to now find the density of, therefore the density of states in k space is always the same. It's how much, if I go, if you give me a certain volume in k space, how many states are there? This is that volume divided by, kind of a 2 pi by L whole cubed. Here I think he's doing a pi by L thing, right? Here he's using a hard wall boundary condition. Sorry, your question?
Yeah, mainly the difference between hard wall and periodic. I found that when you use periodic, you have k is 2 pi. When you don't use periodic and hard wall, you have just pi over L.
Yes.
And then you have the whole quadrant issue. When you do hard wall, you have to divide by 1/8. Why do you not divide by 1/8 when you have periodic?
Yeah, that's a good question. So actually, the 2 pi over L is when you have periodic boundary condition, and so as a result, the volume will become 2 pi by L whole cube. So there's a 2 cube, which will be the 8, right? But in k space, all k's are allowed, because you can have plus k or minus k. In the hard wall boundary condition, now essentially physically you are restricting an electron to be between here and here, and it cannot. So the wave function has to go to 0 at the two edges, at the two ends. It cannot be any finite value. That's the physical meaning of it. Or in other words, the wave has to exactly fit in the box, and it can have no tails outside of the box that you put it in. So if I'm choosing length, just 1D problem, then the wave function must be like this, or at the two ends it must be a 0. That's what you mean, and that's why you get n times some. The wavelength over 2 half wavelength must fit the length, right? And from here you get lambda n is 2L over n, and k is 2 pi by that, so you get 2 pi by that, you get pi over L times n, right? That's not 2 pi by L. So now physically what it's really means is the in a ring, well, let me just say, here's the physical meaning. In a ring, you have a sense of clockwise and counterclockwise. In this, there is no such sense, in a 1D problem. So you can say, well, moving to the left or to the right, and for that, so let me just write down the wave function for you here so that it will kind of become mathematically at least completely clear. So you have e to the power I k x is the wave function for 1D. And so for 1D, the problem is the following. So here's the wave function. There's some coefficients, etc. But the wave function looks like that. Is proportional to that. And if I put x is equal to 0, this should go to 0. And if I put x is equal to L, it should go to 0. Right? That's the physical meaning of it. And so what you x equal to 0 is clearly, okay. So I can say you can see it will be a problem if I put x equal to 0. My origin should be here. So what happens is it restricts the allowed k states to half. It's not, in a ring, the number of k states is twice of that of a linear regime. And because of that, and you kind of triple it in 3 dimensions, you get 8. You have 1/8 the allowed number of states in hardwall compared to, so all the states are here. All these states are here. They are just closer. The same number of states, but they're all in the first quadrant now. And I think you kind of know that already. I'm just saying that we are physically, it is not changing any of these arguments. It's just all the states. I've chosen a model in which all the allowed cases happen to be in the first quadrant and exactly the same number of states as if you were applied periodic. So you can put your origin here or somewhere in the middle of this thing. That's physically what it's doing. So the 8 and all these things will cancel out in the end. And then you'll get the same physical result, be it density of states, be it velocity, anything you find should cancel out in the end. Maybe I'll give you a little, I'll write this up in my notes sometime because this is, I prefer the periodic boundary conditions, and when we need, we will apply the hard wall whenever we need it. So, okay, so, but finding the density of states from the K space is kind of a very important thing. So this is the periodic part of it. So I think in the notes, both of them are treated. And so be sure that, one of the things you can do is, if I give you, here's the energy dispersion, here's parabolic, here's graphene or whatever, I think you had already solved a problem like that. You should be able to find, and you're also solving in this assignment, be able to find what's the density of states from the energy dispersion, right? So you should be able to find those things. So that's one. Velocity. Velocity is kind of the slope in the energy K space, right? And with the velocity, we can find the current that flows in the material. So be sure you can do that, right? That's something we have talked about, and we have solved a couple of problems on that too. So and then there were a few parameters based on that. So we bring in the Fermi function. What is the Fermi level? What is the Fermi wave vector? This is really the fact that Fermi electrons are fermions and exclusion principle has to be satisfied. I stress it again and again because sometimes it does get lost in the discussion, but it's really very interesting that you must fill up, and you fill up these K spaces because of exclusion principle and because of nothing else other than exclusion principle. You have to fill it up, and then you go out and see that if I put in 10 to the power 22 electrons, my K must be this much, right? And the energy of the highest energy must be this much, is Fermi energy. Those highest energy electrons must be moving at this speed. All of that we should be able to calculate from what we have done here, right? So those are the things. So if I give you a metal and say, well, it has this much electrons, you should be immediately able to calculate all of that, because you can find Kf, you can do h squared Kf squared by 2m, you find the electron energy, you can find velocity and all that stuff, right, from here, all of those electrons. So and then okay, so Fermi function, how it changes with temperature, and then 3D, 2D, and 1D, right? So the effect of dimensionality, the density of states, how it changes. It goes from, for a parabolic dispersion, square root of energy for 3D, constant for 2D, and 1 over energy for 1D, right? So those are the things, kind of the main things we have covered till now. Using those, we explained. This part we did in class, how do you explain Drude's law using all this, new machinery of quantum. You can kind of do that. The picture now is you have in K space, but it shifts. So the Fermi function, so you have a, kind of a symmetric and asymmetric, or even an odd function, and you are summing over all of them. So the f of k kind of shifts, and it becomes part of it still remains symmetric, but a part of it becomes asymmetric, and that's what leads to current, right? Because this is the new picture, the quantum mechanical picture of current flow, right? Instead of the classical picture where billiard balls going through and colliding with things, this is the new picture of conductivity, right? Where your electric field is driving the k states, so very important relation is the force, which is charge times electric field, is h bar dk by dt. This is kind of the quantum version of Newton's law of motion, right? Force is mass times acceleration. Here it's not like that. It's the rate of change of momentum, but momentum is h bar k. So it's the Newton's, the quantum version of that. If you allow collisions, then you get this, sort of delta h bar delta k over tau. So this is the damping term in collisions in quantum mechanics. And using this delta k, you solve this, and we were able to find the Drude relationship for conductivity, right? I mean, the quantum version of it, right? So we kind of applied that. So you are using this relation now in this assignment without the damping. One of the problems, I think the second last problem here, is you are given the EK diagram and saying, I'm applying electric field and find out what happens to the electron now. And you will see there, because the band structure is periodic in K space, that we know that classically if I apply a magnetic field, the electron starts going in circles, this cyclotron orbit, that's the physics, Lorentz force, right? If you have an electron which is moving at a certain velocity and you apply a magnetic field, it starts doing circles around the field, right? Classically. And you're solving part of that using quantum, you'll still do circles in quantum. But if you put an electron in a crystal and everything is perfect, and it has a band structure which is periodic in K space, and you apply an electric field, you will see if you solve the problem, which is the second last problem, it'll start doing not circles but periodic motion in real space in an electric field. And that's very weird, but that's what quantum mechanics predicts. It's a Bloch oscillation. It will come out directly from this relation, directly from here. What you have to do is track the K, and with the K comes the energy, which is the band structure, right? So you got okay. So really that part of the story, if you're comfortable with some of these parts, how to find currents, momentum, and some elementary ideas of or rather the effect of dimensionality and density of states, I think we are good for this exam. That's a lot, but I think it's we covered most of it, and it's if you want reading material, I would say just these slides do a pretty good justice to what we have covered in class today and in great detail. And over Saturday I'll post the new set of notes, but there will be a lot to do with what I'm covering now, which is not in the exam. But okay, so. I'm just trying to scan through here and seeing what else. So this is essentially a repeat, 3D, 2D, 1D, and it's done separately for all of these. So please, gonna be comfortable with that. And I think you can, looking at the assignment problems and some of this, you should be able to guess what I'll ask. And you can ask me questions. Is this in the course or something like that? And I'll be happy to answer. The last thing is we do have we decide to have office hours tomorrow. And then we'll do that 5 to 6:30. Okay, in Phillips Hall, same place. All right, and we do have some pizza in the back, so please feel free. And I'm here for a few more minutes. If you have any questions, specific things, I'm happy to answer. Oh yeah, one more thing. Homeworks, first homework, graded homeworks are here, so you can pick them up as well. I had a question. Sure. Yeah. Let me. Material for